Okay, so obviously we had an exam our last class. So my goal is usually to try to get exams graded within a week. I'm not sure if I'm going to make it this time. I'll try for Thursday, but don't hold me to it. So if not Thursday, then definitely next Tuesday, but we'll see how it goes. And in the meantime, we're going to get back on to the material that we finished root finding. So now we're going to start a new topic, which is related to root finding, but is much broader and also far more practical for us as engineers. So let me whoops, click on the wrong buttons here. All right, whoops, that's not going to work. There we go. Okay, so we're going to start the next chapter. It is related in terms of the methods that we use. It's very closely related to root finding. In terms of the applications and how we frame it and the terminology that we're going to use, it'll be quite different. But in terms of the methods actually used to get the results, it's going to be closely related, at least for a little bit, at least until we get to some more complicated situations. One thing you'll notice, which is maybe a bit odd, is normally, just like we've done so far in this class, we start with linear methods first before we do nonlinear methods. However, here I'm going to do the opposite. And the reason is because we can do some interesting nonlinear problems actually more easily than we can do interesting linear programming problems. Linear programming problems, by their very nature, require constraints. And so if we start with nonlinear problems, we can first do nonlinear problems with no constraints. And that will follow very closely with what we've done in mathematics and calculus class and other settings before. And then we can move into linear problems, which require constraints, which makes things a bit more complicated. So it seems backwards, but it actually makes sense to do things this way for reasons that you'll see. So it's a new topic. Let me introduce it. So as I've said, this is very practical. It's actually quite powerful. If you think about engineering, most of engineering is in some way about optimizing something. So you're optimizing a process, you're optimizing a product, you're optimizing a way of doing things. So you're trying to find the best approach. So given a certain set of tools, what's the best approach to accomplishing a task? If I'm leaving class and I'm hungry, what's the best route to take to get those wonderful goodies over at the Commons stacked up in your styrofoam boxes? I feel so bad for you guys with your grab and go meals. It just seems so depressing to me. Anyway, I guess it's no more depressing than me pulling out my brown bag out of my backpack and eating in my office by myself. So it's really no different. But anyway, I guess the point is I do that anyway. So, okay, back to our regularly scheduled program. So the point is, as engineers, whether hungry or not, we are very much all about optimizing something. Oftentimes we use the word optimization kind of loosely. So I think about getting to Commons, I think, well, I'm basically going that direction. And so I'm going to start out in that direction, kind of see how traffic is on State Street and decide where to cross and just kind of take it from there. But what we're talking about is a much more formal and mathematical approach to optimization to indeed find the best way to accomplish something. So that's what this is all about. This is a topic that is not always in undergraduate numerical methods books, not necessarily because it's particularly hard. It's just for whatever reason, it has not been kind of standardized. Undergraduate numerical methods is not standardized on including optimization. However, I think it should because it is so powerful and so useful for us as engineers. So usually what's happening is we're testing some sort of performance or design objective. We have some way of quantifying the performance of our system or our process. We'll talk mainly in terms of systems as mechanical and aerospace engineers. So we have some way to quantify how well it's performing, and we want to accomplish some sort of design objective. We want it to do something really, really well. We want it to do it fast. We want it to do it cheaply, whatever the criteria might be. So we're looking for, again, the best means of accomplishing that particular task. The task itself is captured in some sort of linear or nonlinear algebraic equations. Sorry, not the task, but the system. So the behavior of the system itself is going to be in terms of some sort of algebraic equations, whether linear or nonlinear. So that's going to be like the system model. But then in addition to that, we're going to have something that quantifies the performance. And that'll be our objective function. So we'll call it J, but we'll label it as J, but we'll call it the objective function, or some people sometimes use the term cost function. I'll mostly say objective function, but I'll sprinkle in some cost functions just so you're used to hearing that as well. They're basically the same thing. So that's a separate function. It's still algebraic, but it's a separate function that quantifies how good or bad the system's performance is, or it might quantify the cost of performing something with that system. We've actually already seen an example of optimization in the context of curve fitting. We did not necessarily use that terminology when we discussed curve fitting, but it is a true optimization problem in the sense that we were given a set of points. We defined the total error, which was the sum of the squares of the residuals. That was our objective function. And the objective was to minimize the total error. So to determine the best fit curve, the polynomial, that did the best job of fitting those points. And the way we quantified that was through minimization of the total error. And so that is exactly an optimization problem. It's an excellent example of the kinds of things that we're going to be looking at. All right, now the reason, probably the best reason, well, it's not a good reason, but probably the most common reason why optimization is not always included in undergraduate numerical methods texts is the terminology can get really, really confusing. There are a lot of different options. There's a lot of different scenarios. There's a lot of different terms that are used. So it can get quite confusing. So I'll try to walk us through that in a logical fashion. I think that will make this manageable. So I've highlighted in blue the various kinds of ingredients that can go into an optimization problem. Not every optimization problem has every one of these ingredients, but they are ingredients in all optimization problems. So where we start is with an objective function. We might just have one, so just a j, which is some function of x, or we might have multiple objective functions, so j1, j2, through jm. So we could have one objective function, we could have multiple objective functions, which are all functions of our design variable x. We could have a single design variable x, or we could have a whole bunch of design variables x1 through xn. The optimization could be unconstrained or constrained. So unconstrained obviously means the only thing we're going to be concerned with is what is the x, or what are the x's that minimize our single or multiple objective functions. That's the only consideration we have. If the problem is constrained, that means that those design variables have something else that they need to satisfy. It might be might be the fact that x2 cannot be bigger than 10 for some reason. Maybe x2 is the power of the motor, and the motor cannot exceed, the power of the motor cannot exceed 10. So that's a upper limit on the value of x2. So that's a constraint. They're all going to be algebraic, whether they're linear or nonlinear, but that's a constraint. So we could have an unconstrained optimization problem or a constrained optimization problem. The objective function or functions and the constraint or constraints, if they exist, could be either linear or nonlinear. Maybe you have a nonlinear objective function, but linear system of equations that govern the system, or vice versa, or maybe they're both linear, or maybe they're both nonlinear. All those possibilities can exist. The constraints could be equality constraints, or they could be inequality constraints. So an inequality constraint would be, for example, if I am blasting a rocket into space, the minimum thrust, of course, is 0. The maximum thrust is whatever the maximum thrust is of the rocket engine that I went to Home Depot and bought and stuck at the bottom of my rocket. So there's a range. So it can be anywhere between 0 and that maximum value. So that's an inequality constraint, or it could be an equality constraint. It may be some relationship between the design variables. So for example, maybe it's such that the design variables x1 and x2 are related in a way where x2 is always twice x1 for some reason. So that's an equality constraint. So we have all these options, and they all, you can mix and match. So you could have a single objective function with a whole bunch of design variables that's constrained with nonlinear equality constraints. Or you could have multi-objective functions with one design variable, no constraints, it's nonlinear, and inequality. So all these different combinations, and that's what, again, makes this very complicated. So what we're going to do is start with what we know, which is always a good idea. So we know calculus. We love calculus. We use it every chance we can get in our professional and our personal lives. It is amazing and terrific and life-changing in so many ways. So basically what we're looking for are extremums, which is just a fancy term for minimums and maximums. So I have a function, f of x, that's my j, and I want to find the minimums or maximums in that function because they correspond to some behavior of the system, which is good, which is what I'm looking for. It's the best behavior. And so we are going to use the calculus of extremums in order to find those minimums or maximums. Again, starting with nonlinear equations, because if we have linear functions, a linear function is a straight line. It doesn't have, its maximum is off to infinity and its minimum is off to negative infinity. So that's not very helpful. That's why we need constraints. So for a nonlinear function, which I'll draw on the next slide, we can have minimums and maximums all over the place, and that's what we're looking for. So the end result, the solution is, what are the values of the design variables, which are the independent variables x, x1, x2, x3 through xm, xn, sorry. What are the values of those design variables that make our objective function a minimum or a maximum? That's what we're looking for. So in a calculus context, that just means differentiating our f of x and setting it equal to 0 and determining the values of x for which that is the case. So as I said, we're going to build our intuition by starting off with the cases that follow most directly from calculus, the ones we could do before today without any new mathematics, without any new methods at all. We're just using different terminology. So our cost function or objective function, well, it's just our f of x. That's all it is. X is the independent variable in math. Now we're going to call it our design variable. Makes no difference. Mathematically, it's all the same. So we're going to start with our single objective function, j, that is a function of one variable, one design variable, x, to keep things simple at the start. And then we're going to just show how we can determine, by taking derivatives, setting them equal to 0, how can we determine the optimal value of the design variable x? that gives us the smallest value of j, or f. So that's going to be our goal. The nice thing about doing one-dimensional problems is we can look at them graphically. I can plot my f of x, my j. I can see where the minimums and maximums are. I know roughly where they are, so I can do searches numerically for those minimums and maximums without much difficulty. All right, so again, the connection here is what we're looking for physically is the optimal solution, the best way to accomplish something. Mathematically, that's going to correspond to either a minimum or a maximum in the function. So that's the connection between the physics and the math. Now, generally speaking, we're going to be looking for minimums. Some books do minimums, some books do maximums, most people do minimums. The idea here is that if you really want a maximum, you can set up your methods for finding minimums, but if you really want a maximum, all you have to do is take the negative of your objective function. So if I have an f of x and I'm looking for the maximum, I just take the negative of f of x, then I can look for the minimum. So it really doesn't matter which we decide. You can always make a maximization problem, a minimization problem, and vice versa. So we'll typically think in terms of minimums, finding a minimum, and if the problem dictates we look for a maximum, we'll just take the negative of the objective function. All right, so let's take a look at a generic function f of x that has, let's say it looks something like this. So where it crosses the x-axis, those are the roots, which is what we looked at in the last chapter. So these are values, locations where the value of f of x is 0. Okay, those are the roots. That's not what we're looking for now. Now we are looking for minimums like this, or maximums like this. Now I didn't make my, that's pretty clear. This one's lower on the right here. So I'm going to call that my global minimum, because that's the lowest of all of them. This one is a local minimum, which is kind of self-explanatory. And then we have a maximum, and there is only one maximum, so this is our global maximum. Now, a point like this, so how we test for local minimums and maximums is, as they keep saying, we take the derivative, we set it equal to 0. But a point like this has that property. So f prime of x is equal to 0, just there, just like it is here. And here. And oh, by the way, here. Now, obviously, this point is not a minimum or maximum. It's what we call a stationary point. So the way to think about this is actually all of these are stationary points. They're all points where the derivative is equal to 0. To distinguish between a stationary point like this versus a stationary point like this, which is truly a minimum, we have to look at second derivatives. So I have to look at the curvature. Here, the curvature would be 0 because it's flat. Here, the curvature is positive. It's concave up. So it's a minimum. Here, it's a maximum, so it's concave down, and the curvature of the second derivative is negative. So mathematically, what we say is the necessary condition for an extremum is that the derivative is 0. All 4 of those points qualify in that sense. The sufficient condition is to test the second derivative, the curvature. And that's what eliminates this one as a minimum or a maximum, or again, more generally, an extremum. So does that make sense? So from an optimization point, I don't actually care about this point right here. So even though it does satisfy f prime of 0 is equal to f prime of x is equal to 0, I don't care about it because it's not a minimum or a maximum. Therefore, it's not an optimal solution of my problem in general. So what I'm really looking for is these points, which again requires me to check this curvature of the second derivatives. So that's what's all this is down here. So the roots are just values where f of x is equal to 0. That's not what we're concerned with right now, although you'll see very shortly a connection between roots and extremums. Any point where the slope is 0 is called a stationary point. It may also be a local minimum or maximum, but it may not be. It just depends. So to check whether it's a local minimum, in addition to being a stationary point, we have to check the second derivative, which is the curvature, to see if it's positive. If the curvature is negative, then it's a local maximum. All right, so that's all fine. So in that way, we can determine where the minimums and maximums are. Now, there is no way to, in a calculus sense, there's no way to determine which minimum in this case is global or local. I'd have to actually check the value. I'd have to see, well, what is the value of f at x here versus f of x here? Well, this one's lower. They're both minimums, but this one's lower, so it's a global. But I don't necessarily know what's going on for the rest of the function. So mathematically, all we can say is where the minimums and maximums are, as well as the stationary points, which we don't care about. In terms of local versus global, I need a global method. I need to be able to plot the function or something like that to be able to determine that. So typically, we won't be able to formally determine whether it's a local minimum or not, or global minimum. Okay, now here's the connection with root finding. So I have my f of x. It has roots where f of x is equal to 0. And it has stationary points where f prime of x is equal to 0. So to connect the two, what I can do is if I just take the derivative of f of x, so f prime of x, I set that equal to 0, well, that's now a root finding problem. But it's rather than being a root finding problem for f of x is equal to 0, it's a root finding problem for f prime of x is equal to 0. So one way to find the minimums and maximums is to start off with my function f of x, differentiate it so I get its slope, f prime of x, and then determine the roots of f prime of x, because the roots of f prime of x are the extremums of f of x. That's a connection between root finding and optimization of nonlinear systems. Okay, so that leads us to things like Newton's method or bisection method in order to determine these roots, which then correspond to the minimums and maximums, which are our optimal solutions. So you'll see all that come together when we start talking about methods themselves. Okay, let's talk more specifically about nonlinear programming, which is what we've been introducing, but now we're going to talk about it more specifically. First, I have to explain this term programming. So when we think of programming today, what we think of is computer programming. So I program in Python, I program in Fortran, I program in C++. So that's how we use the term programming. The way it's used in the context of optimization, it's basically synonymous with optimization, and that's for historical reasons. It came out of World War II. So the military during World War II would do optimization problems. They needed to get supplies and troops and so forth to various parts of the world. It was a world war, right? So they could get all these supplies and troops to different places of the world, and they wanted to do it in the optimal way, the fastest way, the most effective way in terms of fuel utilization. So they developed these algorithms. And so many of the algorithms that we use today had their origin in these programming problems. What we would today call supply chain or logistics, they called programs. So we still today use this term, linear programming, nonlinear programming. So whenever you see that, just equate it with optimization. Nothing to do with computer programming as we think of it. It's just optimization. So that's where that came from. So let's think in terms of our functions or function, whether it's one function or multiple functions, in terms of one variable or multiple design variables. We'll call that our objective function, or some people call it the cost function. I like to say that pessimists call them cost functions because all they care about, just tell me how much it's going to cost. Whereas the optimists among us call it an objective. What am I trying to accomplish? What's the good thing I'm trying to accomplish in this optimization test? So optimization or objective function, that's what we optimists call it, as opposed to you pessimists, where we call it a cost function. That's not really true, but anyway, I like it. Sounds good. And then again, our variables, they are the independent variables from a mathematical point of view, but now we're going to call them our design variables, or sometimes people will call them in certain contexts the control variables. So again, either whatever you call them, they are the independent variables for the problem. F is the dependent variable for the problem, but we're now going to call that our objective function. I warned you. I said one of the things that makes this a bit difficult is all the terminology and the jargon. And there's often more than one term, as you can see, used for each thing. It depends on the context as to whether you call a design variable or a control variable or a objective or a cost function. So it's just something we have to kind of get used to. All right, so I've said this before, but the idea here is rather than considering the linear problems first, which are normally the easiest, I'm actually going to start with nonlinear problems because I don't have to worry about constraints. I can look at nonlinear problems without constraints first, then we'll do nonlinear problems with constraints, and then we'll do linear problems with constraints. There is no such thing as linear problems without constraints because, as I said, you have to have a constraint, otherwise things go to infinity or negative infinity. All right, so having said that, we're going to be looking for minimums, or in some cases maximums, of our either objective function or functions, which are functions of one or more variables. But to start with, they're going to be nonlinear functions. As I said, it's often the case that there are constraints. So if I'm going to walk from here to Commons Cafeteria, then I'm going to make sure that I'm careful, because I'm a conformist, to cross State Street at a proper pedestrian crossing. So that's a constraint. I can't just cross anywhere I want. I need to cross at a pedestrian crossway. Also, because I'm a conformist, I'm not going to walk through the grass. I'm going to walk on the sidewalk. So I'm constrained in the path that I take and where I can cross State Street and so forth. Now, in terms of speed, I'm not going to sprint. I mean, the food is amazing, but it's not that amazing. So I'm not going to be sprinting to lunch unless I'm trying to get ahead of you guys, because you guys all take too long to get your pizza and build your tacos. And so do they still we used to have Taco Thursday. It made no sense to me. Do they still have a taco day? Of course, there's probably not now, because you have to build your own, right? You can't do that under COVID. I never understood. Why would you call it Taco Thursday? Why not Taco, I don't know. Is there another day of the week that starts with a hard T sound? Let me think. Oh yeah, Tuesday. Taco Tuesday, everyone. Ay, ay, ay. Okay, every day is pizza day, right? You can have pizza. That's the great thing about college. You can have pizza for breakfast, lunch, and dinner. Breakfast pizza. What could be better? Oh, pizza, pizza, pizza. All right. Anyway, where was I? Oh yeah, I'm optimizing my route to my Taco Tuesday. So there are very often constraints, but we'll start with the unconstrained problem first. Then we'll look at how we incorporate constraints. And the way that we do that is to use Lagrange multipliers. You may have seen them before, maybe you haven't. Either way, I'll explain them, and they're not very difficult. But that's how we will incorporate constraints into our optimization problem. All right, so first, unconstrained optimization. So we have a function of x or we have a function of multiple x's, either way, but we just have one objective function. And we are looking for the value of x, or the values of all the x's, for which f of x, j, has a minimum. All right, but there's no constraints. So I'm literally, I can plot it. If it's an f of x, I can plot it as I did schematically just a moment ago. And I can look for where are the minimums, where are the maximums, those are the optimal solutions I'm looking for. So we're going to start off thinking that. So we can visualize it graphically. We can plot it using MATLAB or Python. We can see exactly how it behaves. Now there's two general techniques. The first technique is for easier problems, not so complicated. And the second technique, which is a numerical method, which is iterative, for more complicated methods. So we'll do examples of both. We'll use the first method when we can, because it's easier. And we'll use the second method when we must, because it's more general. So the first approach is to just directly evaluate the first derivative. So you take df dx is set it equal to 0, f prime of x is set equal to 0, and then determine the value of x for which that is true. And if necessary, get the mathematical pun there because it's really a sufficient condition. If necessary, I can also check the second derivative. So I can determine the curvature to see whether indeed it is a minimum or a maximum. So that's just straight from calculus, just applying calculus directly to our optimization problems to determine where a minimum might occur. The second approach, which is more general and can be applied to more complicated situations, we will differentiate the objective function and then calculate the roots of f prime of x is equal to 0, as I just said a moment ago. So rather than the roots of f of x is equal to 0, we're going to determine the roots of f prime of x is equal to 0, because those points correspond to stationary points and potential optimal points, maximums, minimums of our original f of x function. And then we can do things like Newton's method. So we'll come back and we'll see Newton's method again. And so we'll do examples of both of these. We'll look at both of these basic approaches. All right, so let's look at a simple example. This is a one-dimensional objective function. And what that means is the one dimensionality means it only has one independent variable, x. So there's only one design variable. In this case, it is the miles per hour. So that's the thing we're going to change, the miles per hour. So what we're going to do is look at the fuel economy of a car. This is the actual data from a particular vehicle. So they just, at different speeds, they measured the fuel economy in miles per gallon. And so you see the raw data right there. And what we want to do is determine what is the speed that gives me the maximum fuel economy. So if I am driving from point A to point B, and if my objective is to get there using the least amount of fuel, what speed should I drive at? If my objective is to get there as quickly as I can, well, that's obviously different, because that will mean the highest speed possible. And then what's your constraint? Well, for my grandmother, the constraint was the speed limit. For most of us, the constraint is the fastest we think we can go without getting caught above the speed limit. And I did not say that. This will not be posted on YouTube. Sorry. Okay, so we have miles per gallon. That's the objective function as a function of the speed, miles per hour. So our F is the fuel economy, the J, and the X is the speed, miles per hour. Now, what we can do, since we have raw data like this, is we could use our curve fitting, because we love curve fitting. It's so much fun. And we didn't get to do enough of it on the exam. So we clearly must do more. So we can do a polynomial curve fit, for example. This is a quadratic curve fit. So this is the best fit parabola. This is the best fit parabola. I'm so excited about this. And you can see it's not that great. Doesn't do a very good job here, doesn't do a very good job here. So we could up the order of the polynomial. So this is a third order, so a cubic polynomial curve fit, same underlying data points, but you can see it does a much better job of fitting to those points. Then once you get the curve fit, that becomes your J. That's your f of x. So that is the thing we want to find an extremum of. Now, in this case, we want to find a maximum. If I wanted to find a minimum, I could just take the negative of f of x and find the minimum, but we'll just leave it as a maximum. It really doesn't matter. Okay, so great. So I have a reasonably good representation of the data. And in fact, I got that by doing an optimization problem through polynomial curve fitting. So like I said, in some cases, in simple cases, I can simply take my single objective function, f of x. I can differentiate with respect to the design variable x. Now here, the f and the x have physical meaning. One is the fuel economy and one is the speed. I can set it equal to 0, and I can determine the value of x that gives me that extremum, in this case, the maximum. Here, I can do that. I can't always do that, but here I can. I can differentiate the function, set it equal to 0, and determine the value of x, the speed that gives me that maximum fuel economy. In this case, I have a cubic polynomial. So this is a third order polynomial. When I differentiate it, of course, it becomes a quadratic. I set that equal to 0. I can find the values of x for which it's equal to 0. Those are determined from the quadratic equation. Of course, that's not normally the case, but in this case, it is. So I can literally just do what I said, take the derivative, set it equal to 0, I'll get a quadratic, then I can use the quadratic equation in order to determine the value of x or values of x that give me an extremum. Normally, of course, that will not be possible. So normally I'm not going to be able to solve for analytically the values of x that give me minimums or maximums in my objective function. We'll have to use some other technique, namely a numerical method such as Newton's method. But for now, it's very straightforward. So here's my f prime of x. So I took my cubic curve fit and I just differentiated it. Lickety split, no problem. It's again second order. So I do have the quadratic equation from which I could get the value, or in this case, two values of x for which that's an extremum. But instead, let's talk about how we would use a root finding technique. So the root finding technique, remember, is applied to that function f prime of x, not f of x, but f prime of x. Because once again, the roots of f prime of x are the same as the extremums of f of x, which is what we're looking for. So I can get my f prime of x, which I have right here, and then I could use Newton's method to determine, whatever my favorite root finding method is, to determine the value of x for which f prime of x is indeed equal to 0. Now I know analytically there's actually two of them because it's a quadratic. Where is the other one? Okay, obviously here's one. Where's the other one? Well, I don't know. I mean, this is a cubic, right? So it goes like this somehow eventually. And so the other one's right here. But obviously within my range of data, this is the one I'm looking for. This one is outside the range of data. That's not the one I'm looking for. So even though there's mathematically two, clearly it's this one that I'm seeking. Okay, so let's remind ourselves how Newton's method works. It's an iterative method. We start with an initial guess for x, where the root is. And we start with k is equal to 0. The k is my iteration number. I calculate delta x for that iteration. And then I use that to correct my initial guess to get a better value of x at the next iterate, the k plus first iterate. How do we get the delta x? Remember, that was minus f over f prime. So how did we get that? We got that from the Taylor series. So we wrote the Taylor series of f of x around a point where we're doing the approximation. And then we solve for delta x. We truncated it, and then we solve for delta x, and this is what we got. So that's our general Newton's method approach. So we calculate delta x from this expression, and then we use that to correct our last approximation for the location of the root. Now, in this case, this is a little bit confusing, but in this case, because we're looking for the root of f prime of x, all of these derivatives have to be upgraded by 1. So this f in Newton's root finding technique becomes an f prime. This f prime becomes an f double prime. Does that make sense? Because now I'm looking for the roots of f prime of x rather than the roots of f of x. So that's why these get upgraded from 0 and 1 to 1 and 2. But otherwise, it's the same idea. Get your delta x from this expression, use that to correct your last approximation to get your new approximation for the location of the root of f prime of x, which is the extremum of f of x. Okay, said that, yep, okay. So the problem with Newton's method in general is you do need to evaluate the first and second derivatives analytically. Now, for simple problems like we have here, that's no problem. I can take as many derivatives of that cubic polynomial as you want because it's very simple. Even I can do that. In more complicated situations where there's multiple objectives and there's a whole bunch of design variables, well, you got to take a derivative with respect to each of the design variables of each of the objective functions, and it can get pretty messy. So Newton's method can get messy, but in this case, it's fine. We just have one function of one variable. So we just have first derivative and second derivative of our objective function. So when you do that, you determine that the maximum occurs when x is equal to 41.0677 miles per hour. And you look back as a sanity check and you say 41.77, yeah, that looks about right. You know, you can argue from the data, it looks like this point's a little higher. And if you zoom in on that and you say, well, gee, I don't know, it gave me this point as the maximum of my curve fit, but maybe it really does have a little bit of a kick there in this range of speeds where I get, for some reason, a little improvement. Or it could just be that there's some measurement error and this really should be smoothed out and this is the correct value. That's an argument for another day. That's an argument for the validity of our curve fit. Once we've done the curve fit, then it's just a matter of, for that function, where does the maximum occur? Simple as that. Again, just to say it one more time, normally we'll be looking for minimums. In this case, we were looking for a maximum. It was obvious because I could plot it that was the case. But if in fact you want a maximum, but you've designed all of your algorithms to look for minimums, then all you have to do is take the negative of your cost function. That's all you have to do. So instead of f of x, you have minus f of x. It literally just flips it upside down. And so any maximums become minimums and you're good to go. Again, obviously you'll end up with the same result, doesn't matter. Now, if I have multi-dimensional objective function, so this means I have still one. So always think, how many objective functions do I have? One or more. How many design variables do I have? One or more. So first we did one objective function with one design variable. Now let's look at one objective function with multiple design variables. If it's two instead of one, I can still plot it rather than just a one-dimensional plot. It's now a surface plot, like so. And so you can see in terms of x and y, you can see the value of f of x at each of those points. So you see there's a maximum right here, there's a minimum here, there's a minimum here. This one looks lower than this one, so this is a local minimum, whereas this one's a global minimum. And I only see one maximum, so that's the global maximum right there. So same idea, it's just now multiple dimensions, but the same process. But now we're going to have to differentiate with respect to 2 variables instead of just 1. So it's more of the same basic mathematics, but a little bit more difficult in terms of the implementation of it, actually carrying it out. All right, so if we're looking for a minimum, we're actually looking for this one. But you can clearly see where you start the iterative process. If I start the iterative process here to the left of this ridge, well, it's going to take me down into this hole. If I start on this side, it'll take me down into this one. So if I start here, it's going to find this one. I start here, it's going to find this one. So clearly it depends on where I start. But that's the same in 1 dimension or 20 dimensions. It doesn't matter. It just depends on where we start. Okay, so let's take a look at an example with 3 design variables. So I still have 1 objective function f, but now I have 3 design variables x1, x2, and x3. And I want to find a minimum. So I want to determine the x1, x2, x3 variables, the design variables, for which f, as a function of those 3 variables, is a minimum. Now, this function in this particular example, nothing special about this, but in this particular example, it's a rational function of polynomials. So it's the numerator is a polynomial and the denominator is a polynomial. It's one polynomial over another. Nothing special about that. That's just what this particular objective function f of x happens to be. We'll call the numerator f1 and the denominator f2 just to keep our lives a little bit simple. So start from scratch. Calculus. First thing we do, we take our f and we want to differentiate with respect to each of the independent or design variables x1, x2, and x3. So let's think about that. So I have partial f, partial xn is equal to 0, where n is either 1, 2, or 3. So I'm going to have to take 3 first order partial derivatives. Now remember, f is f1 over f2, the numerator over the denominator. So if I differentiate f, where f is a ratio of f1 over f2, then it's going to take on this particular form. This is from the quotient rule. So it's nothing extraordinary here, just straight from calculus. It looks messy, but it's just straight from calculus. So I have partial f1 partial xn, x1, x2, x3, minus f1 over f2 partial xn, all over f2, and that has to be equal to 0. That, again, that's just applying the quotient rule to this f is f1 over f2. That's all it is. So now I have 3 equations, because n is 1, 2, and 3. So now I have 3 equations that I set equal to 0. Now, if I let lambda, I just pick some random Greek letter, there's a bunch of them, and I just picked a random Greek letter, just so happened to pick lambda, no particular reason, and I'm going to call that my f, which is f1 over f2. Now, why did I do that? Well, here's an f1 over f2, so I'm going to call that lambda. And you'll see why that's helpful in a moment. So I've just rewritten this quotient rule in this form, where lambda is f1 over f2. Okay, so I just have to take the partial derivative of f1 with x2, f1 being the numerator, xn, x1, x2, x3, and then the partial derivative of the denominator, f2, with x1, x2, x3, fine. And that's going to give me a bunch of equations. It turns out to be a system of equations, 3 equations for my 3 unknowns, x1, x2, and x3. So here so they're on the same slide. I've repeated f1 and f2. This is the numerator, and this is the denominator, just same as we had in the last slide, just repeat them. And then I take my partial derivatives. So partial f1, partial x1, x2, x3, partial f2, partial x1, x2, x3. So let's just walk through a few of these. So here's f1. So let's take the partial derivative with respect to x1. First term gives me a 2x1, 2x1. Second term gives me a 6x2, 6x2. No x1s here, no x1s there. partial f1, partial x2. No x2s in the first term. Second term is 6x1, 6x1. Third term is 8x2s, 8x2, and there's no x2s in the last term. Finally, with respect to x3, no x3s, no x3s, no x3s. Differentiate this with respect to x3, that's just 2x3, 2x3. So you can see it's a bit tedious, but it's not hard. And then the same thing for the f2, which is x1 squared plus x2 squared plus x3 squared. With respect to x1, that's just 2x1. This term's gone. This term's gone. With respect to x2, it's 2x2. This term's gone. This term's gone. And with respect to x3, this term's gone. This term's gone. And we have 2x3. Again, not hard, just a bit tedious. So now I can write down my three equations from equation 6.2. So partial f1, partial x1, minus lambda partial f2 partial x1 is equal to 0. And then for x2, x2, and then x3, x3. And that gives me 1, 2, 3 equations. 2x1 plus x2 minus lambda 2x2 is equal to 0. First equation. This is the second equation, 6x1 plus 8x2 minus lambda times 2x2 is equal to 0. And then 2x3 minus lambda 2x3 is equal to 0. So 3 equations for my 3 unknowns. But oh my, look at my 3 equations. This looks familiar. That's an eigenproblem. Not because I randomly chose lambda as my Greek letter, but I chose my lambda as my Greek letter because I knew it was going to turn out to be an eigenproblem. So I have a 3 by 3 coefficient matrix, which comes from here, 1, 3, and 0. So 1, 3, and 0. And then 3, 4, and 0. 3, 4, 0. And finally, 0, 0, 1. 0, 0, 1. And then on the right-hand side, bring this over, and bring this over. And I have the 2's have all canceled. So I just have x1, x2, x3 on the right-hand side all times lambda. So this is simply an eigenproblem. The lambda, what is lambda? Oh, that's just f1, f2. So I get 3 eigenvalues. Those are going to give me 3 values of x1, x2, sorry, f1 over f2, so f. And corresponding to that will be 3 eigenvectors, which are my x1, x2, x3 combinations. So I'm going to have 3 lambda and x pairs. First lambda, first x, second lambda, second x, third lambda, third x, as you'll see in a moment. So it turns out that this is always the case. I didn't pick any special problem to make this happen. If you have a rational function of polynomials and you do optimization on it, you will always end up with an eigenproblem to solve. So I gave you a whole bunch of applications where eigenproblems come up, such as finding principal stresses and principal strains. And here's now another one when we're doing optimization of rational polynomials. All right, great. So I can solve this and get the values of f, those are the lambdas, and the corresponding x1, x2, x3 triplets. Those are the values of the corresponding design variables that give me those minimum or maximum values of f. So in other words, the eigenvalues are the possible values of the objective function. There'll be 3 of them. And then the corresponding 3 eigenvectors will give us the corresponding values of the design variables. So again, math, physics. So the math is, it just happens to be an eigenproblem. And then what do they represent physically in the context of this optimization setting? Okay, so let's take a look at those. I got these using MATLAB or Mathematica. So you get lambda 1 is 1, here's lambda 2, Here's lambda 3. It's 1/2 times the quantity 5 plus or 5 minus 3 times root 5. Here are the corresponding numerical values if you care. And then corresponding to each of these is the eigenvector 0, 0, 1 for lambda is equal to 1. This is the corresponding eigenvector for this eigenvalue. And this is the corresponding eigenvector for this eigenvalue. So the question is, well, which one do I care about? If I'm looking for a minimum, I have 1, 5.8, and minus 0.8541. Well, what's the smallest one? Well, it's this one. So lambda 3 gives me the smallest value of f. That's the optimal solution that I'm looking for. And the corresponding vector, eigenvector x3, gives me the value of x1, x2, and x3 that corresponds to that minimum. So here's x1, x2 is 1, and x3 is 0. So always be looking for that. And of course, I'm always liking to point those things out. What's the relationship between the physical problem that we're trying to solve as engineers and the mathematical problem that corresponds to that physical problem? So the mathematical problem in this case ends up being an eigenvalue eigenvector problem, but the eigenvalues and eigenvectors have a physical connotation, physical relationship to the original problem. All right, so x3 and lambda 3 correspond to the minimum because this is the smallest of my 3 eigenvalues. All right, any questions about any of this so far? So no constraints yet, just nonlinear objective functions. First, an objective function of 1 variable, now an objective function of 3 variables, but still no constraints. Any questions, comments, or concerns? Okay. So you can see one of the great things about optimization, which is also one of the hard things, is that it draws from a lot of the mathematics and numerical methods that we have already learned. So it's rooted in differential calculus. So taking derivatives and setting them equal to 0. So that's differential calculus. Sometimes when we do that, we end up with eigenproblems. Not all the time, not every time, but sometimes we end up with eigenproblems, which of course is a linear algebra issue. Curve fitting was necessary to take my raw data and to turn it into a functional behavior that I could then do my differentiation on for the optimization. And then root finding to actually determine the optimal solutions, the minimum or maximum. So we're drawing on a lot of different math as well as numerical methods when we do these. So I like it for that reason because it pulls all these things together, but obviously it can get a little bit confusing at times because of all the different scenarios that are possible and all of the different methods and mathematics that we're pulling in to show how to, to actually solve these problems. Okay, so let's look at a method, not necessarily the best method, but a method for determining, back to our 2D objective function, for determining the minimums. So it's called the method of steepest descent, which is exactly what it sounds like. So you just imagine yourself standing on this topographical map someplace, and you're just going to go down in the direction of steepest descent. So you stand at your location and you look around you and you determine the direction that has the steepest slope. You can think of it as standing there and dumping a cup of water and seeing where the water goes. The water is going to follow the steepest slope downward. So that's the method of steepest descent. It's very intuitive. It's easy to see what it's intending to do, but it's quite slow. It can be very tedious to actually carry out for complicated problems. So basically, as long as you start somewhere in the particular bowl that you have the minimum, you will end up at the minimum eventually. It may take a while to get there, but eventually you will get there. So it's essentially a multidimensional version of Newton's method. It's actually not as good as Newton's method, and we will generalize Newton's method for these types of problems later, probably in our next class on Thursday. But it is essentially a multidimensional version of what we've done so far for the 1D Newton's method. So there's really two steps. The first step is to determine the best direction to proceed down the bowl. And that's just as simple as looking at the slopes. So you take the gradient, and the gradient is in the direction of maximum downward slope. Actually, negative gradient is in the direction of negative. Yeah, you know what I mean. Dump the water, goes down. That's the whole point. So that's step one, is to determine which direction to proceed down the hill, down the bowl. Then the second step is to determine how far to proceed. So in other words, what is the step size? So which direction to go, and then how far to step in that direction. That's exactly what the method is doing. So it is a Newton-like method. Newton's method determines which direction to go. It's in the direction of the negative tangent, and then it tells you, delta x tells you what step to take in that particular direction. Now we're just thinking about it in a two-dimensional rather than a one-dimensional context. Okay, so let's say, for example, we have a single objective function with n, capital N, design variables. So one objective function with a whole bunch of variables. So we're going to need the first derivative of f with respect to each of the variables, partial f, partial x1, partial f, partial x2, 3, all the way up to n. And then we set all of those equal to 0. So in our last example, little n was 3, well, sorry, big N was 3. And so we had 3 of these derivatives to evaluate and set equal to 0. In the general context, this is called the gradient of f. The gradient of f. The gradient is, mathematically, the direction of steepest descent. It's actually the negative of the gradient, but that's the direction of the steepest descent. So if I evaluate the gradient, which is this, that's just a vector of all of those first partial derivatives. F with respect to x1, f with respect to x2, down to f with respect to xn. Then, if I set that vector equal to 0, notice this is bold, it's the 0 vector. If I set that equal to 0, that is my necessary condition for an extremum. All the derivatives are being set to 0. This is nothing new from what we've done before. All I'm doing is couching it in terms of vectors and matrices, because now I have lots of design variables, and so it's going to be easier for us to think in terms of vectors and matrices as opposed to just a whole bunch of equations. It's exactly 100% mathematically equivalent. It'll just be a linear algebra way, vector matrix way to look at things rather than just a list of equations. Okay, 2 basic approaches. There are non-gradient methods, and there are gradient methods. So what we've been thinking in terms of so far are gradient methods, or so far we've talked about the descent method of greatest descent. So that's a gradient method. Gradient methods are very intuitive from the sense that, okay, I can look at this plot of my two-dimensional function. I can see what I want to do. I want to follow the train down into the bottom of this bowl. How do I get there? Well, I descend into the bowl by following the gradients. So they're very intuitive. However, as you can see, they involve evaluating lots of derivatives. And so sometimes that's a problem. And in that case, you can use what are called non-gradient methods, or sometimes they're called direct methods. So obviously, those are methods that do not require evaluation of the derivatives of the objective function. So there are some advantages to that, but we'll primarily focus on the second approach where we do use the gradient methods or descent methods. So these are going to be like Newton type methods, but now in potentially multiple dimensions, not just one dimension. So we're going to have first order derivatives, as we already have. That's what makes up the gradient vector. We're also going to have second order derivatives. Those are the curvatures. So just like in the 1D case, to get the necessary condition, we had to look at the curvature to see whether it was a minimum or a maximum. So we're still going to have to do that. But now we're going to have a whole bunch of them, because it's a whole bunch of second derivatives of f with respect to each of the x1s, x2s, as well as x1 and x2 together. So that's called the Hessian. I'll show you what that looks like in a moment. Those are going to have to be calculated analytically. So again, this is where it gets tedious. And the more x variables you have, the more derivatives you have to evaluate to fill up your gradient vector and your Hessian matrix. So again, not hard, not difficult, but yes, indeed, it is quite tedious. So we could do this for an objective function, which is an analytical function. That'll be our primary focus in this chapter. But it could also be done on discrete data, where you have to use, for example, finite difference methods to get those derivatives. We'll save that for a later chapter. So again, let's come back to the method of steepest descent. It's a gradient or descent method. It's in the name, so that makes sense. And we're going to just walk through then the process of how we carry this out. But again, intuitively, you're just thinking, I'm on a mountainside. I want to get down to the lowest point of the valley. What direction do I go? And what is the step size that I take for each step, each iteration of this process? All right, so here are the two main steps. These are the same steps in Newton's method, but now written more generally for, in this case, so we can picture it in our minds, a two-dimensional, or broadly, an n-dimensional problem. Obviously, if n is beyond 2, I can't picture it graphically in my mind. I can't picture it as a surface in space, but it's the same basic idea. So the first step is to determine the direction to proceed. The second step is to determine how far to proceed. What is the step size for each iteration? So it's always the case that the negative of the gradient points in the, it's a vector, and it points in the direction of the steepest descent. So again, that's the direction that the water will run if I dump it at that location. So P is the direction, that is the negative of the gradient of F. Now, here's where it gets messy. So I'm going to have to evaluate this gradient every time I get a new set of values of X. So I start on my initial guess. That's my point here, or 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 here, wherever I start. And then I'm going to iterate. Take one step, K increments by 1, and 2, and 3, and 4. K goes from 0 to however many steps I'm willing to take. I have enough time before Taco Tuesday to get some lunch and get re-energized. So that is the first step. So that's to calculate P. P is in the direction of steepest descent at each iteration. Then I need to calculate the delta x to determine how far to proceed in the direction of the vector P. We're going to follow a straight line. So I'm going to determine the direction P, and then I'm going to go in a straight line until something happens, until a logical time at which to no longer go in that direction. And that is exactly what you think. We're going to take the step size such that I find the minimum along my straight descent path. Now again, always just think of yourself on a three-dimensional topographical map standing on the side of a mountain. So I find the direction, step 1, with the negative, the largest negative gradient. Fine, that tells me which way to go. And then I'm going to keep going, keep going, keep going as long as I'm continuing to go down. As soon as I start to go back up again, I've clearly reached a negative ridge, a minimum ridge. It may not be the minimum yet, but at least for that direction, that one-dimensional direction, that's the minimum. And then I'll stop at that location, and then I'll do it again. At that location, I'll look around me to determine what is the direction of steepest descent. Then I'll go in that direction as long as I keep going down. As soon as it starts going up again, I stop. And then that's my new location to do the same process. So again, it's a slow process. It's a tedious process. It's not the fastest process, but it's the simplest conceptually to think about. Literally just these two steps. Once you have your delta x for each iteration, just like Newton's method, you update your estimate, your approximation for the minimum. So you start off with your original approximation for the minimum. You get your step size delta x, and that gives you a new one. Nothing to it. All right, some comments about this. Essentially, the method of steepest descent converts a multi-dimensional descent problem into a series of 1D minimum seeking problems. So again, I at each step one, I can go in any direction I want. But once I pick the direction, it's now a one-dimensional problem because I'm just going to go in that one direction as long as I go down. So it converts the multi-dimensional problem into a 1D problem at each iteration. That's the basic concept. That's the basic idea behind the method of steepest descent. So once again, you're hiking into a valley. And so that would not be the best way to get the bottom of the valley, but you would eventually get there as long as the train is always going down. But it is going to be somewhat meandering because I could be standing at a location and I say, well, the water runs this way. That's the direction of maximum negative gradient. But I can see very clearly that the minimum in the valley is over there. So of course, in practice, we would do this, right? But what this method is saying is all I can go based on is what I see right at my current location. Go this direction, it's the steepest descent, and then I just walk in that direction until I get to the bottom of that one-dimensional valley. And then presumably it's going to tell me at that point to turn left towards the actual minimum. So it's kind of meandering. It's not a straight line path. Okay, the speed is only linear, so it's first order, whereas you'll remember Newton's method is quadratic or second order. So conceptually, this is easier than Newton's method. It's actually easier to program than Newton's method, but it is slower. So there is a price to be paid for the simplicity. So you're trading off simplicity for for speed of execution. Oh, Dilbert. We love Dilbert. What's Dilbert have to say? Well, it's Wally again. Wally, have you made any progress coding your module? Oh, I love this one. So this is for you coding geeks. And I've said this before, and I will say it probably a few more times this semester. We often view coding as a chore. We often view coding as kind of a rote and tedious activity. But in fact, coding does encompass a lot of creativity. And so I think it's important to understand that. I don't enjoy coding for the sake of coding. I enjoy coding to create a new tool that I can use to help learn something. But even in the context of coding itself, there is a sense with which there is a lot of room for creativity. And that's what this cartoon is sort of getting at. So the manager, pointy-haired boss, asks if you're making any progress on coding your module. And of course, Wally, who's the engineer, the programmer, says rightly that progress is difficult to measure when you're coding. he says, well, you could just measure the lines of code that I produce, right? So you could just have a little dashboard on the manager's computer that shows how many lines of code per hour each programmer produces. But that would reward inefficiency. That would reward me doing the same task with more lines of code. So as he reflects here, as he's sipping on his coffee, he says, the art of this job is binding the rare moments of inspiration to knowledge and machines. And so again, that's the whole idea of it being a creative endeavor. In fact, just a minute ago, I could feel the inspiration welling up inside of me, but then you interrupted me with your naive question and the moment was lost. Maybe you should go back to your office and reflect on the damage you've done here today. And there goes the one person who has a less of a real job than I do. So anyway, my point again is embrace the element of creativity in the act of programming. There's a lot more room for it than you might expect. Okay, so we'll stop there. We'll pick up Newton's method next time. So Newton's method is a little bit more complicated, but we've seen it before, but it's faster. It's second order accurate. It's, second order convergence rate. So it's faster than the method of steepest descent. And we'll talk about that next time. So I think I sent an email yesterday, problem set 4 is posted on Blackboard, due on Friday, all based on root finding methods. And I'll try to get the exams back as soon as I can. So we'll see you Thursday. Thank you.